Alright, I want to review the things we've been talking about with sampling distributions and the binomial distribution. See if I can put it all together. These are things that from chapters 2, 8, and 9 in the book. First of all, situations where we use norm CDF. Or we would look up in a normal table if we weren't using a calculator. First of all, whenever we use normal CDF, it's a good idea to sketch a normal curve and figure out what we're looking for. If we're looking for everything to the left of a point, then we do the norm CDF from -10 to whatever the point is. If we're looking to the right, we would do from whatever the point is to 10. And then if we're looking in between, we just go from Z1 to Z2. So that would be in between Z1 to Z2. Okay, so here are a bunch of situations where we've learned to use this normal distribution. I'll just go. Number one is if we take, we're taking just one observation from a normal population. So let's say that the Redskins average 280 yards a game on offense with a standard deviation of 55 yards, and we want to know what is the probability that they in one game, in the next game, gain over 400 yards. Okay, so we would let Z equals x minus mu over sigma, and x in this case is 400, mu is the 280, sigma is 55, and then we'd take whatever that is. If I'd use 390, I'd get a nice round number, wouldn't I? But anyway, we'd take the normal CDF from that Z to 10, since we're looking for greater than, and that would be our probability. That would be the answer. Okay, so that's the first use. That was chapter 2. And then another use, and this is in some sense, this first one's a special case of this. In a small sample from I'll just call it a normal population, meaning normally distributed. Well, I'll just write it out. Normally distributed population. What is the probability that a sample average will fall somewhere? And I'll give an example of what I mean by somewhere. Again, let's just say the Redskins average 280, standard deviation of 55, and now they're going to play, let's say, in 6 games. What is the probability that they average less than 300? Okay, we could have said average less than, we could have said greater than, we could have said in between, we could do a bunch of things. So but let's say less than 300. So the average we call x bar, and our new formula is Z. Okay, let me just back up a little bit. The mu of x bar is equal to mu. So the mean of that we'd expect for the sample mean would be the true mean. Sigma of x bar is equal to sigma over the square root of n, where n is our sample size. So we have mu of x bar in this case is equal to 280, and sigma of x bar is equal to 55, and since we're doing 6 games, over the square root of 6. And what we're trying to see is, okay, here's 280, here's 300, but we're looking for less than. So we're wanting to see if our x bar will be less than 300. So z is equal to 300 minus 280. Z is equal to, let me just generalize it, x bar minus mu x bar all over sigma x bar, which in turn, let's just remember that sigma of x bar is sigma over square root of n. So sometimes I'll just write it out as x bar minus mu of x bar over sigma over, or x bar minus mu, since mu of x bar is always equal to mu. Over sigma over square root of n. So I'll often just shortcut write it x bar minus mu over sigma over the square root of n. Yeah. Okay. Now, so x bar is 300. That's our. We're trying to see if we're going to get less than 300. Minus mu 280 over sigma over square root of n. 55 over the square root of 6. That would be our z, and because we're looking at less than, we would do norm CDF from -10 to z, if we get there. Okay, so that's the second example. The third use for norm CDF, 1, 2, 3, is in a large sample. For now, I'll just say greater than 30, but it might have to be larger. From a population that's not normally distributed. So let's say we're doing a population. We're talking about the salary of NFL football players, and the mean from the population is, let's say, 4.1 million. That's probably high, actually. Standard deviation of 2.7, and we want to talk about what will happen if we take, let's say, a sample of 50. Okay, they're not necessarily normally distributed. In fact, it would be highly skewed. Probably have a few players who are earning way up here, 10, 15 million as quarterbacks, and then a lot of players earning $1 million or less down here. So, but anyway, we take a sample of 50, and we, once again, if we have a large enough sample, the mu of x bar is going to be the true mu, okay, and the sigma of x bar is going to be sigma over square root of n. So we have 50 as our sample size, 2.7 is our sigma, and then we could ask what's the probability that in our sample. Let's do a between one just to give an example of that. What's the probability that x bar, or our sample mean, is between 3.7 and 4.5 million? So we would take z is equal to x bar minus mu. I'm just going to do it the short way, mu over sigma over square root of n. So x bar will take a 3.7, we'll take one of the points, minus the true mean was 4.1, all over sigma I said was 2.7 over square root of 50. And that's z1. And then z2 we get from plugging in 4.5 in there, we get a z2, and then we can do a norm CDF from z1 to z2. So that's our third case, a large sample from a population. And we're basically doing the same math as we did in a small sample where we know the population was normal. Now we have a large population that wasn't necessarily normal. And the last case is another case where the population isn't normal. It's called the sample proportion. Okay, and there we can use this. The rule of thumb in the book is that n times p has to be greater than 10 and n times 1 minus p has to be greater than 10 in order for this normal approximation to work. So that's our definition of a large sample size in this case. So let's say we're sampling in Montgomery County for political affiliation, and the true proportion of Democrats we'll call P is equal to 0.6. And we're going to take a sample of 200 voters, and we want to know what's the probability that we'll get between 0.58 and 0.61. Notice I picked an asymmetric one, so we'll have to calculate two z's here. And for the binomial setting, the binary, where we're doing a sample proportion, so it's Democrat or not Democrat, yes or no type of thing. Z in this case is equal to p hat minus mu of p hat all over sigma over square root of n, and mu of p hat is equal to the true p. And in these chapters we're pretending that we know what the true p is, so sigma is equal to square root of p times 1 minus p. So when you shorten this up, you get z is equal to p hat, that's the sample proportion, minus p all over square root of p times 1 minus p over n. Okay, so in this case our p is 0.6. Our first p hat, that is one boundary for the sample mean, is 0.58. So z1 is equal to 0.58 minus the true one, p, 0.6, over square root of 0.6 times 1 minus 0.6 all over 200. And then z2, our second boundary, will be the second one, 0.61 minus 0.6 all over square root of 0.6, 1 minus 0.6 all over 200. And then we can use this normal approximation, normal CDF, from z1 to z2 to get the probability that we draw a sample of 200 that where the sample proportion falls between 0.58 and 0.61. Okay, so that's all the uses of the normal. Let me give you a case where we use invnorm, and that's when we solve for n. So suppose we want to say, in this last example, and we could do this actually with any of these examples, we could ask how large a sample size in order to get a 95% chance that p hat will be between 0.58 and 0.62. And this time I'm going to use a symmetric one, because that'll be easier to do. So we have a z star, which we get by, let's just sketch. So if we have 95% in the middle, between 0.58 and 0.62, we want 95% to be in the middle. That means there's 2.5% on each side. So in terms of percentiles, this is 0.025 and 0.975. So if we set so we do, let's z, we'll call this z star equals inv norm 0.025, whatever that is. I'm going to say that's about 2. You can check it. Okay, and so we set 2, if that's what it is, equals 0.58 minus 0.60 over square root of 0.6 times 1 minus 0.6 over n. And the whole point of this is we're trying to get n, how large a sample size. So this is a case of the missing n, and we would just use algebra to get it out of there. So we'd say 2 times the square root of 0.6. I'm going to do this slowly. 1 minus 0.6 over n is equal to 0.58 minus 0.60. So I just move this over to the left side. Now I can square both sides, and I get 4 times 0.6, 1 minus 0.6 over n is equal to, and we got to square this, that's negative 0.02 squared, so it's 0.0004 maybe? Whatever that is, 0.02 squared. I don't promise that I got that right. And then we would say multiply by n and then divide by whatever this thing is over here. So we get 4 times 0.6 times 1 minus 0.6 is equal to let's say 0.02 squared times n, and then we divide by the 0.02 squared, and then we'll come up with our answer. And that's how we solve for a case of the missing n. Okay, the other thing that we've learned is exact calculations for the binomial. So now we're no longer doing approximations, but we can do exact. And the first case is when we're counting the number of successes. So let's say we were counting the number of Democrats and this is, you have to use this in a small sample. So let's say we're going to count the number of Democrats in a sample of 11 voters. Okay, and the probability of being a Democrat in Montgomery County is 0.6. So the average, the mu of this mean number of Democrats will be 0.6 times 11 is equal to 0.66. The standard deviation is the square root of, now this time we don't put it in the denominator, it's in the numerator. So that's the square root of 0.66 times 1 minus p 1 minus 0.6. So whatever that works out to be. That's the standard deviation. Then if we want to say what's the probability of getting exactly 5 in our sample, then that would be binom PDF. N is 11, P is 0.6, K is 5. And then finally, if we want to get up to and including 5, up to and including 5, we do binom CDF 11.65. And just be careful if we wanted to say more than 5, what's the probability of getting more than 5, then we do 1 minus binom CDF 11.65, and greater than or equal to 5 is a different number. It would be 1 minus binom CDF 11.64, because now we don't want to rule out the 5. So we would use 1 minus binom CDF 11.64. So that's, and I'll just make a final note that you can calculate sample proportions with large samples exactly using binom CDF. The one challenge is the case of the missing n-type problems that we just did. If you use the binom, you end up having to use guess and check. So I think that's one reason to just use to get in the habit of using the normal approximation. But it is true that you don't necessarily need the normal approximation to get the right answer, and in fact you get more exact answers if you use the binomial distribution. So that's our review for this, for what we've been learning.